In this video, we're going to go ahead and introduce the concept of resonance. I want to impress upon you guys on the importance of this concept. Resonance plays the foundation of a lot of other ideas that we're going to cover later, from acid-base chemistry, mechanisms, SN1, SN2, so on, and then reactions, reagents, products, right? And so we have to really master this idea, and we have to build in essentially that confidence and have zero doubt when it comes to this idea and this concept moving forward. Now, in order to understand resonance, we need to start out at Lewis structures. So we've already done Lewis structures in the past, but I'm going to go ahead and give you an example where we can start off with. And the example that we have here today is going to be CH3 CO2 minus. Now, we go through and look at the valence electrons of each of these atoms. And so we have 4 valence electrons for carbon, 1 valence electron for hydrogens. There are 3 hydrogens, and then another 4 valence electrons for carbon, and oxygen has 6 valence electrons, and there's 2 of them. We can count the overall number of electrons, but I'll just go ahead and draw the structures without them for now. I'll go ahead and also put this negative charge in red. And now, negative charge indicates that we have an additional electron present in somewhere in the molecule. So let's go ahead and start to brainstorm some ways we can connect this. Let's put a carbon with the 4 valence electron it needs around it, and then we'll go ahead and connect it to this middle carbon and give that 4 valence electrons. And then we'll connect the oxygen. Oxygen has 6 valence electrons, and I'll put an oxygen there as well. Now you might ask, how did I know to go ahead and put the oxygens in that position? When it comes to putting the oxygens, if I put the oxygens between 2 carbons, I would figure out that that would not be the ideal structure to meet all of the octets, so on and so forth. And so you got to play around with it until you get to essentially where you need to go. And so here are the hydrogens, which each have a valence electron, making it a duet. So now let's count the electrons around each molecule. So we know this carbon right here has 8 electrons, so it is happy with its octet. This carbon in the middle of everything has 2, 4, 6, 7 electrons around it. It is not happy because it does not have an octet. This oxygen down here has 2, 4, 6 in the bond, and then 7 total. So it's also not happy with this specific arrangement as it stands. And the same thing with this oxygen on the end. We have 2 in the bond, 4, 6, and a 7 electron. Now, let's go ahead and see if there's another way I can arrange things so that way I can make things happen. Let's say I take the electrons there, the individual electrons on the carbon and the oxygen, and I put them both into a bond. So I'll go ahead and erase them. These aren't really technically arrow pushing, so I don't want to give it arrow pushing, and we'll learn more about arrow pushing later. But I put those 2 electrons that were on the carbon and the oxygen respectively in this bond. Now, if I go ahead and erase the counts and recount, I'll have essentially 8 electrons on this oxygen and 8 electrons on this carbon. So those are happy atoms now because they've each achieved their octet. The problem though is we still have an electron that is missing, and essentially because we have 7 electrons and we need 8. So where might we get that 8th electron? If we remember, we had a negative charge up here. So that means the molecule has overall an additional electron. So we're going to stick that additional electron there, and guess what? Now we are happy with 8 on this molecule, or on this atom. And so we've met our octet rule because of that additional electron. Now the question arises, is there an additional valid Lewis structure. And the answer is yes, there is. So I'm going to go ahead and try to brainstorm another possible arrangement of this structure. And so let's go ahead and actually, I'll kind of save you guys the having to essentially brainstorm multiple position. And let's go ahead and put the double bond down here with that oxygen on the bottom and the lone pairs around the oxygen on the right, and then we'll throw in the hydrogens around that carbon. Now let's go ahead and count. I have 8 electrons here, so that's Metis octet. I have 8 electrons there. That's also Metis octet. I have 8 electrons there. That's its octet, and then obviously our carbon there surrounded by the hydrogens has 8 electrons. So that's Metis octet. So we are happy with this structure as well. So we have 2 valid Lewis structures for this molecule. And so what we do in order to represent the fact that we have 2 valid Lewis structures is we recognize that they are resonance. So we draw a resonance arrow. So a resonance arrow, it's very important that you don't mistake it with an equilibrium arrow. Resonance means that both of these structures are actually correct at the exact same time. The actual correct structure is both, at the same time. Now, equilibrium arrows would say that you would go back and forth between, so if I draw an equilibrium arrow, it would say you would go back and forth between this molecule and that, but that is not correct. With resonance, it's indicating that we are actually these 2 molecules at the exact same time. We are not going back and forth between them. So don't confuse equilibrium arrows with resonance arrows. Again, resonance means that we are actually those 2 structures at the exact same time. Now, the next question that arises is, what is the definition, the formal definition essentially, of resonance structures? And now that we've done an example, we can kind of go ahead and flesh that out. So the first thing that we want to think about is that in both of these structures, I'll go ahead and clean this up a bit, get rid of the octets, and equilibrium arrow. And I'll go ahead and say that both of these are valid. They're both valid structures. So this is a valid structure, and that is a valid Lewis structure. So both of these are valid structures. So the definition of resonance comprises valid, I'll say Lewis Now, whenever we say resonance, we already know it's plural because resonance, again, indicates multiple structures involved. Now, there can be more than 2 resonance structures. So essentially, they're all going to be valid Lewis structures. If I have 3, 4, 5, whatever, they would all be valid Lewis structures. So that's the first thing. They've got to be valid Lewis structures. The second thing is that they have the same connectivity of atoms, right? And so let's essentially indicate that by going through and looking at the connectivity. So we have a carbon, let's go back. We have a carbon surrounded by hydrogens in both structures. You see that? Carbon surrounded by hydrogens in both structures. Now we also have a C-C bond in both structures. We have a CO bond in both structures. In this structure, it's only a single bond. Here it's a double bond, right? So, but at least we have a CO bond, one of them, in both structures. Here, same thing. We have a CO bond here and a CO bond there. Yes, this one has a double bond, but in this one has a CO bond. So at least both of them share a CO bond, even if they don't share the positioning of the double bond, right? And so the same connectivity of atoms. So we'll say the same backbone in all resonance structures. Okay. The third and last condition of having a resonance structure is that we have different positions for multiple bonds so double and triple bonds, and then unshared electrons. And so let's take a look, and we'll highlight it in blue. If we look, we have essentially a double bond here, and then the position is now there. So it changes across the different structures. So the positions, different positions for multiple bonds. In this case, we have double. So you see how the double bond changes positions. Same thing with the, let's go ahead and make that one electron that was extra in red. And let's take a look now at those lone pairs. So here, an unshared electron is on this right oxygen, but now those unshared electrons are on that bottom oxygen. So they moved positions. So we have different positions for multiple bonds and for unshared electrons. That's what constitutes resonance structures. These three things. They're both valid fluid structures. They have the same connectivity of atoms, the same backbones essentially, but different positions for multiple bonds and for unshared electrons. Now the question next arises, we have to answer, is how do we represent the correct structure if there are multiple valid structures at the exact same time? So let me write that out. If there are multiple valid Lewis structures at the exact same time. Now the answer to this question is resonance hybrid. Now there are two steps to drawing a resonance hybrid. The first step, step one, is to identify the same backbones present in both structures. All right, so let's take a look. I'll actually go ahead and redraw all of this so that way we can get a better idea of how to draw the resonance hybrid. And so we have go ahead and put all of my electrons in. Put the lone pairs on, then the resonance arrow, and we'll do the same thing. And we're going to go ahead and remember the negative charge. Let's see if I remembered it up here. I did not. And so we got to get really good at our autocorrect mechanisms. And so it becomes more intentional, less intentional as you move on because you have so much practice with it. But at the very beginning, you have to go back through and make sure that you've copied over the correct number of hydrogens and also the number of the charges as well. So let's make sure that I follow and I practice what I preach by going ahead and putting the hydrogens there. And so here are my resonance structures. Step one, identify the same backbone. So what's the backbone? These hydrogens around this carbon, the CO bond, one bond there, right? And so let's take a look. We have those are in common, all of these H's are also in common. So this essentially is that. They're in both structures. The CO bond down here is in both structures. Oh, CO bond is in both structures, right? So let me get rid of that and make it a little cleaner. And so at least one CO bond is there, even though we have a double bond in this case and a double bond over here, right? And so the backbone, what it will look like, that is present in both molecules is that, right? Now, let's take a look at what lone pairs are present in this molecule. So I'll change the color to yellow. Here we have 2 lone pairs. And here we have 3 lone pairs. Here we have 3 lone pairs. Here we have 2 lone pairs. So we need what's universal to every atom. And so here, even though we have 3, in this structure we only have 2. So we would only be able to copy 2 over. Here we have 3, but in this structure we only have 2. So we're only able to copy 2 over. We need to figure out what's common to both structures. And so 2 lone pairs, even though this has a third, is common in this case, and then 2 lone pairs is common in that case, right? And so that's the first step. And I'll go ahead and actually put these in green so we can recognize that these are part of the same backbone, right? So that was step 1. Step 2 in identifying the resonance hybrid is going to be to identify what's different in both structures. So identify, we'll say different positions of multiple bonds and unshared electrons, right? And then we're going to say, and assign partial negative or partial positive or dashed lines. Right? And so let's now look at this. So here we have the double bond at the bottom. Here we have the double bond at the right. So what I'll go ahead and do for the double bond at the bottom, I'm going to draw a dashed line to represent that there would be a double bond in the bottom in one structure, but not in the other. Here, I'm going to draw my dashed line over here to indicate in this structure to the left, we have a double bond there, but not in that structure to the right. So I'll go ahead and erase these lines. You should be able to make that connection now. And then same thing with the lone pairs. In this case, my lone pair is on my right oxygen, whereas here it's on my bottom. And so we have a negative charge right here on the right and a negative charge on the left. Let me clean this up a bit. And a negative charge here. So on the left molecule, the negative charge is at the bottom oxygen. So I'll indicate it's a partial negative. It is not fully negative because on the right structure, there is no negative. I actually drew an extra lone pair there. That should not be there. There we go. And so on the bottom oxygen, it's going to be negatively charged. Here, we're going to do a partial negative because on the right structure, it's a full negative, but on the left structure, it's neutral. And so this becomes our resonance hybrid. It's a way to represent that we are actually both structures at the same time. It indicates that the correct overall structure is multiple resonance structures at the same time. So that is resonance hybrid, and again, this will play a crucial role in the rest of our understanding of organic chemistry.